If we were tracking back a little bit, if we wanted to find velocity instead, we go back to here and see that velocity is going to be equal to square root of gm over r. Now, an interesting thing about that is that all these values, well, not all these, g and m and pi, of course, are all constants. This is the mass of whatever object's being orbited. G is a fundamental constant, pi is pi. So for a given radius, orbital radius, there's only one period, only one velocity that allows you to maintain an orbit at that radius. So that's good to know. And if you're given a radius, you can figure out period and velocity using these relationships. If you forget these equations, they're not given on the formula sheet for the exam, you can always go back to Newton's second law, and you guys know centripetal acceleration can be v squared over r or 4 pi squared r over period squared. So just a couple examples that we can do with that. Earth's average orbital, oh there it is, 1.5 times 10 to the 11th meters. I was right about my power of 10. So one astronomical unit is 1.5 times 10 to the 11th meters. That's the Earth's average orbital radius. We want to determine the mass of the sun. Well, what can we do with that? We know the orbital radius, we know g, we know the period of the Earth's orbit around the sun. It's about 365.25 days. So we're going to have to do a little unit conversion here. So 365.25 days times 24 hours in a day times 3,600 seconds in an hour. That gets us 3,155,7,600 seconds. That's how many seconds are in a year. Random interesting fact, this is not that far away from being pi times 10 to the 7th. Yeah. You guys probably don't care, but I think that's interesting. And so once we have the time, then we can just plug stuff in. I'd actually like to rearrange my equation a little bit to solve for the mass of the sun. Actually, I'll go back to up here, t squared gm over 4 pi squared r cubed. Then the mass is equal to 4 pi squared r cubed over t squared g. And then we can plug numbers in from there. 4 pi squared 1.5 times 10 to the 11th cubed over, I'm going to store this as just write t because that's a big number, and g is 6.67 times 10 to the minus 11th. So we can punch that in, 4 pi squared 1.5 times 10 to the 11th cubed divided by answer squared times 6.67 negative 11, leaving us with about 2.0 times 10 to the 30th kilograms. If you look it up on Google or in your textbook, it'll say either 2.0 or 1.99 times 10 to the 30th kilograms. That's pretty darn close. It's interesting to note that the mass of the Earth does not come into this calculation at all. That's interesting. There's just another example. Moon Triton orbits Neptune. An average distance of that gives you mass. Find the orbital period. An orbital velocity. Period. We know is 2 pi r to the 3 halves over root g m. That's 2 pi 3.55 times 10 to the 8th to the 3 halves over square root 6.67 times 10 to the minus 11th times the mass of Neptune, 1.02 times 10 to the 26th. I will leave that calculation as an exercise for you. The orbital speed is from above just root gm over r. squared is 6.67 times 10 to the minus 11th times 1.02 times 10 to the 26th over 3.55 times 10 to the 8th. So these calculations are pretty straightforward. What can be tricky about them is all these powers of 10 that are difficult to keep track of. Now let's take a look at this. So satellite is moving in a circular orbit, radius r, and the Earth, period t, speed v. Instead, it's in a radius 2r. What would be its period and speed? Well, Kepler's third law says period squared is proportional to radius cubed. So the original period is t, the original radius is r, new radius is 2r, so we can say period squared over new period squared is equal to radius cubed over new radius cubed. So what does that give us? That gives us 2 cubed is 8. 8r cubed period squared is equal to r cubed times new period squared. And we can see that the new period then is equal to square root 8, which is 2 root 2 times the old period. From our equation here, we can see that velocity is proportional to 1 over root radius. So old velocity over new velocity would be equal to 1 over old radius over 1 over new radius. And we flippity, and we cross multiply. Well, if we take the reciprocals and multiply, then we get root 2r over root r, so the r's cancel out, and we're left with v over root 2 equals v2. So the speed decreases by a factor of root 2, the period increases by a factor of 2 root 2. One thing that we people do with satellites, put them in orbit, for some purposes, weather and communications particularly, it's useful to put satellites in a geosynchronous orbit around the Earth, meaning the satellite orbits the Earth with a period of 24 hours. So synchronized, geo, Earth, synchronous. So it's synchronized with the Earth. It orbits around the same amount of time it takes the Earth to rotate once. So if you put in a satellite in a geosynchronous orbit above the equator, then it's directly above the same point on Earth all the time, which can be handy. So yeah, how far above the surface of the Earth must a geosynchronous satellite orbit? Above the surface, that's tricky. So we can use the full equation for Kepler's third law. 2 pi, actually I'm going to jump back to period squared equals 4 pi squared radius cubed over gm. And we're finding radius, so I'll solve for radius. So radius would be 2gm period squared over 4 pi squared to the third root. And then we could plug in numbers and calculate. This one's a little bit obnoxious. G is 6.67 times 10 to the minus 11th. Mass of Earth, 5.97 times 10 to the 24th. Period is 24 hours, so that's 24 times 3600 squared all over 4 pi squared. So you can calculate that. The only thing to note is the question is how far above the surface of the Earth must it be? So r is the distance from the center of the Earth. So that is equal to, in this case, is equal to the radius of Earth plus distance from the surface. So you'd have to subtract 6,370 kilometers to figure out how far above the surface of the Earth it has to be. And to find velocity, we can just use the same equation from before, root gm over r. And then use your radius calculation, the results that you got over here, this r. Take this whole big number and plug it in for r. plug in G and M, and you can calculate a number. Something else that takes Kepler's laws into account is if you want to shift things around in orbit. So if a satellite's in a circular orbit, but you want to move it to a bigger circular orbit, what's the most efficient way to do this? You might think that you want to, rocket straight upward, but that's not actually the best way to go about this. So, according to Kepler's third law, we know the greater speed corresponds to an orbit of greater radius. I'm sorry, that's the other way around. A greater speed corresponds to an orbit of smaller radius. But from Kepler's second law, we know that objects move fastest when they're in their orbits when they're closest to the sun or Earth or whatever, and slowest when they are farther away. So let's think about that. How can you make a circular orbit elliptical? Well, if we change the speed. If we increase the speed at one point, then the object, the satellite, will sweep out a greater area than it was a minute ago. And then, so in order to maintain that at the other opposite end of the orbit, the satellite will be farther away, because if you get it going faster all of a sudden, a greater speed, if you get it going faster all of a sudden, then it's going to have to slow down. It can't stay in the same orbital radius with a greater speed. And so here's your Earth, whatever, the satellite's in a circular orbit. Right here, say you suddenly are going faster. Now, in order for gravity to slow it back down, it's going to wind up taking longer, so it'll be pushed out into this elliptical orbit, with this point being on the major axis of the ellipse. So that makes it into an elliptical orbit. If you slow it down, it'll make an ellipse that is smaller, so it'll get closer at the other end of the orbit if you slow it down. How can you make an elliptical orbit circular? Well, do the same thing, or the opposite thing. You change speed at one of these, well, at any point really, but again, you can change the speed. If you speed up here, now obviously the satellite is moving faster, so it'll take gravity longer to pull it in toward Earth, and so then you create a bigger circular orbit. So if you fire your rockets twice at opposite ends of a diameter, then you go from a smaller circle to a bigger circle.